What's up guys, Math Olympian here, and today we're going to be taking a look at a simple and clean IMO problem about sequences. Now keep in mind that when I say simple, I'm talking in Math Olympiad terms, so it's still quite challenging, and you shouldn't feel frustrated if you don't get it first time around. So, the problem says, for each integer a0 greater than 1, define the sequence a0, a1, a2, so on, for n greater than equal to 0, as an plus 1 equals square root of an if square root of an is an integer, and an plus 3 otherwise. So the question is asking us to determine all values of a0 such that there exists a number a, such that an equals a for infinitely many values of n. Now what this last part basically means is that we want the sequence to repeat, enter an infinite loop. So it's essentially asking us to find all values of a0 such that the sequence eventually becomes an infinite loop. So if you want to give this problem a try yourself first, you can pause the video right now. Now, so a good rule of thumb to start with these questions that have sequences and patterns is to just try some small numbers. So here it's asking us about the value of a0, so we can just plug in some small values of a0 and see what happens. So if we try 2, 2 goes to 5 because square root of 2 is not an integer, and then it goes to 8 for the same reason, to 13, and so on and so forth. And you'll find that it doesn't really seem to ever take the second option where square root of an is an integer. If we try 3, then 3 goes to 6, 6 goes to 9, but square root of 9 is 3, is an integer, so it goes to 3 again, and it just gets stuck in an infinite loop of 3, 6, 9. And if we try 4, square root of 4 is 2. So 4 goes to 2, which goes to 5, and it's just the same as the first one. So if we take a look at our 3, 6, 9 example, it is one of the only ones that end up in an infinite loop. So if we try this with other multiples of 3, so let's say we start with 30. Then it goes to 36, which goes to 6, and then to 9 to 3. It ends up in the same loop. So we have a hypothesis that maybe all multiples of 3, when a0 is a multiple of 3, then it will end back up in an infinite loop, specifically 3, 6, 9. Well, so that's our hypothesis. And okay, instead of saying multiple of 3, we could say a0 is congruent to 0 mod 3. And we could also extend this so we could do casework on congruent to 1 mod 3 and 2 mod 3. Well, this is a pretty natural thing to do because, well, firstly it takes care of the case of a multiple of 3 that ends in an infinite loop. And also, if you recall, the second case when square root of an is not an integer, it's an plus 3, so that doesn't really change anything if it's mod 3, because 3 is a multiple of 3. Well, so we're going to split into 3 cases, 0 mod 3, 1 mod 3, and 2 mod 3. And so we can revise our original expression. So the top still stays the same, but the bottom, an plus 3, is actually congruent to an mod 3, because the 3 doesn't matter in mod 3. Well, so with this observation, let's first take a look at a0 is congruent to 2 mod 3. Now you may be wondering, why are we doing a0 congruent to 2 mod 3? Well, that's a good question, and this is based on an observation. Well, if we take a look at the squares mod 3, so you can have 0, 1, every number is 0, 1, or 2 mod 3. Well, 0 squared is 0 mod 3, 1 squared is 1 mod 3, and 2 squared is 1 mod 3. So as you'll notice, there's no square that is 2 mod 3. So what this means is that when a number is 2 mod 3, its square root is not going to be an integer. So if we look back at this, it's never going to be the first one because square root an is never going to be an integer. So the expression is, our sequence just turns into an plus 1 equals an plus 3, an plus 3. Well, obviously this will just keep increasing, and it's not gonna go back into a loop. So this doesn't satisfy the problem's question, the problem's condition, which is that it will have to end up in an infinite loop. So a0 is congruent to 2 mod 3, Doesn't work. Okay, so back to our original case, which is a0 is congruent to 0 mod 3. Well, so let's take a look at an example here. 30, 36, 6, 9, 3. Well, our hypothesis is that the sequence generally decreases and it eventually reaches the 3, 6, 9 loop. Because if you look here, we start from 30, but after we reach 36, it goes back down to 6. So it's like a decrease. Even though it's like it goes up from 30 to 33 to 36, but it eventually comes back down. So how do we prove this? Well, let's just let q be the smallest integer such that 3q squared is greater than or equal to 3p. So here, like, 3p is just our standard, like, number. Let's just say a something, an is 3p. Then we're defining q to be 3q squared is greater than or equal to 3p. Well, so if we observe here, then we'll notice that for all p greater than 1, q is less than or equal to p minus 1. Well, p greater than 1 is because p equals 1 is trivial. Then p equals 1, then 3p is just 3. So it's just in the 3, 6, 9 loop. So we can let p greater than 1. Well, for this case, let's say 30. Well, then p will be 10. So 3p is 30. And what q would be here? Q would be 2, because 3 times 2 is 6, and 6 squared is the smallest number that can be greater than 30, like for q, the smallest q. Well, we'll notice that q is less than or equal to p minus 1, which in that case is that 2 is less than or equal to 10 minus 1, which is 9. Well, that's true. So why is this true? Well, we'll prove this now. So what we're trying to prove is that for all p greater than 1, q is less than or equal to p minus 1. Well, let's first recall that q is the smallest integer such that 3q squared is greater than 3p, greater than or equal to 3p. So let's visualize this with a number line. And we have 3p here. So essentially, let's let these lines be squares that are greater than 3p, that are also multiples of 3. So what we're saying is that 3q squared is right here. So a neat observation here is that when q is equal to p minus 1, if we can prove that when q equal to p minus 1, this is true, then we've essentially proven this. Well, why is that? So let's say p minus 1 is somewhere here. So this is 3 times p minus 1 squared. Well, if q was greater than p minus 1, so q would be somewhere off here, then this p minus 1 would actually be less than 3q squared. 3p minus 1 squared is less than 3q squared. But by definition, q is the smallest integer, and p minus 1 cannot be smaller than q. So therefore, if we can prove this, then q is less than or equal to p minus 1. So we just want to prove that 3p minus 1 squared, this entire thing squared, sorry, is greater than or equal to 3p. So from here on out, it's just algebra. So we have 9p minus 1 squared is greater than or equal to 3p, which is 9p squared minus 18p plus 9 is greater than or equal to 3p, which results to 3p squared minus 7p plus 3 is greater than or equal to 0. And this is just a quadratic inequality. And how we solve this is first by finding the roots of the quadratic expression with the quadratic formula, which is p equals 7 plus or minus 7 squared minus 4 times 3 times 3, square root of that, over 2 times 3, which is equal to 7 plus or minus square root of 13 over 6. So the two roots are 7 minus square root 13 over 6 and 7 plus square root 13 over 6. So we can actually graph that here. So 7 over 6, let's say it's here, then 7 minus square root 13 over 6 will be around here. So square root 13 is between 3 and 4, like about 3.5. So it will be around here. and 7 plus square root 13 over 6 is there. And since the leading term here is 3p squared, the parabola faces upwards. So we would have ourselves something like that. That would be a graph. So basically, when is this greater than or equal to 0? So all parts here and all parts here. Well, keep in mind that this is 7 plus square root 13 over 6, which would result to about 1.5. It's definitely less than 2. So our original assumption was that p is greater than 1. So if this was 1, then p has to be on this side. So for all p greater than 1, and since 2 is here, everything that's greater than 2 is already in this shaded region here. So for all p greater than 1, this holds true. So we've already proved what we sought out to prove. So that's just QED. And so we've shown that when q equals p minus 1, this holds true. And therefore, q is less than or equal to p minus 1. Okay, so since we've proven that for p greater than 1, q is less than or equal to p minus 1, we'll notice that if we start from 3p, it will keep increasing by 3 until we reach 3q squared. Well, this is because since 3q squared is the smallest square greater than 3p, then we don't have to worry about anything in between because and there's no squares in between, so it's all just plus 3. So we get to 3q squared, and then we will just take the square root route to get to 3q. But since 3q is less than or equal to p minus 1, we, over this process, we went from 3q to 3p, so we decreased by at least 3. So following this logic, we can go from 3p to 3q, which decreases, and then we can treat 3q as a new 3p. So it goes on another journey, like another sequence of operations again until it reaches 3r, which is smaller than 3q, and so on and so forth until we eventually reach 3, which we already know is in the 369 loop. So this will eventually reach the 369 loop. So everything, whenever we start with a0 is congruent to 0 mod 3, it will keep decreasing until it reaches 369, and then that's an infinite loop. So we've proven that for a0 is congruent to 0 mod 3, it satisfies the problem's conditions because we want an infinite loop. Okay, so for the last case, a0 is congruent to 1 mod 3. Now, we've mentioned before that we can have 2 squared is congruent to 1 mod 3, or 1 squared is congruent to 1 mod 3. Well, so here, when we start with a0 is congruent to 1 mod 3, we increase by 3 until we get to a square number. Well, that square number cannot be, the square root of that square number cannot be 2 mod 3. Because if it's 2 mod 3, then the number will just keep on increasing like we've seen before. And then you can't get into an infinite loop. So, an, no matter what it is, it always has to be 1 mod 3. If it's 2 mod 3, then we will not go into an infinite loop. So with similar logic to the previous case, we can let q be the smallest integer such that 3q plus 1 squared is greater than or equal to 3p plus 1. So here 3p plus 1 is again like our arbitrary an. And then we define q to be like the smallest square that's greater than that. Okay, so we can make another observation, the same observation actually. For p greater than 1, which is non-trivial p, we have q is less than or equal to p minus 1. So we can basically use the same algebra to to prove that this is true, which we'll do now. Okay, so now we want to prove that for all p greater than 1, q is less than or equal to p minus 1 again. And here q is the smallest integer such that 3q plus 1 squared is greater than or equal to 3p plus 1. So this is almost the exact same setup as last time, and the solution is basically almost the exact same. So last time we said that if we prove that q equals p minus 1 satisfies this, then we can prove what we want. And that's also true for this one, for the same reasons. So if we have a number line and 3p plus 1 here, and if we prove that this is true, then 3 times p minus 1 plus 1 squared is somewhere here. And so q cannot be greater than that. So q has to be less than or equal to p minus 1. Yeah, so again, we just have to prove that 3 times p minus 1 plus 1 squared is greater than or equal to 3p plus 1. And again, it's pure algebra. You can skip this part if you want to. And we get 9p squared minus 18p plus 9 plus 1 plus 6p minus 6 is greater than or equal to 3p plus 1. And so we can cancel some stuff out here. This results in 4. This is negative 12p, negative 15p, and this is 3. So we get 9p squared minus 15p plus 3 is greater than or equal to 0, which, if we divide by 3, is 3p squared minus 5p plus 1 is greater than or equal to 0. So, we can't seem to factor this, so we might have to use the quadratic formula again. So we get that the roots are p equals 5 plus or minus 5 squared minus 4 times 3 times 1 over 2 times 3, which is equal to 5 plus or minus square root of 13 over 6. So last time it was 7 plus or minus square root of 13, and now it's 5 plus or minus square root of 13. So it's just shifted a little bit over to the left from last time. So it will be, the roots would be around here, where 1 is around, p equals 1 is around here, and p equals 2 is here. So this equation, inequality, will be satisfied in this shaded area, which covers everything for p is greater than 1. So again, we have proved this, QED. And so for q equals p minus 1, it does satisfy this, and therefore this is true. So since we've proven that q is less than or equal to p minus 1, we can do the same thing as before. So 3p plus 1 will enter this sequence of operations until it reaches 3q plus 1, which is less than 3p plus 1, strictly less than. And then it goes 3r plus 1, so on and so forth, until it reaches 4, which is when p is equal to 1. So 4, as we've seen before, goes to 2, which goes to like 5a, and like so on. Like it just doesn't repeat. So the sequence will keep decreasing until it reaches 4 and 2, which is 2 mod 3, and the sequence will increase indefinitely without a loop. So a0 congruent to 1 does not congruent to 1 mod 3 does not satisfy the problem's conditions. So in conclusion, we've split this up. So in conclusion, we've made an observation about like how mod 3 will affect this question. So then we split it up into 3 cases of a0 is congruent to 1, 2, and 0 mod 3. And we found that a0 is congruent to 0 mod 3 is the only one that works. So our answer is a0 is congruent to 0 mod 3, or like a0 is 3k, if you want to put it that way. So that's our answer. Thank you for watching this video, and see you in the next one.